Deep in the heart of the rugged Himalayas, the Chenab Railway Bridge has officially shattered every record to become the highest railway bridge in the world, standing at a height of 359 meters above the Chenab River. To create this monumental structure in the harsh valleys of Jammu and Kashmir, India had to invest up to $5 billion and devote a full 2 decades of construction. But how were humans able to transport 30,000 tons of steel across sheer mountain cliffs where no roads existed? And how were they able to suspend steel components weighing dozens of tons in midair and assemble them with millimeter-level precision without any support from the valley floor? In today's video, join Mandarin Tech as we decode the extraordinary construction process of the Chenab Bridge, where humans use steel to overcome the fury of nature. The Chenab Rail Bridge is a crucial part of the 272-kilometer mountain railway known as the Udhampur-Srinagar-Baramulla Rail Link, a decades-long infrastructure project aimed at connecting the Kashmir Valley with India's national railway network. For many years, the region's rugged high mountain terrain left it almost completely isolated from the rest of the country during the winter. And for the railway line to truly reach this valley, engineers were forced to overcome the most severe natural bottleneck along the entire route, the Chenab River Gorge. It is at this very location that the Chenab Rail Bridge became the decisive link for the entire Trans-Himalayan railway line. Crossing a gorge hundreds of meters deep not only opened the way for the first railway line to reach Kashmir, but also marked an important step forward in the ambition to extend modern infrastructure deep into one of the most rugged high mountain regions in Asia. Before even thinking about suspending massive steel components across a span of 359 meters in midair, engineers had to confront the first physical barrier: site accessibility. The construction location was completely isolated within a natural gorge, where the earliest survey teams could only reach the area by traveling upstream, by boat, or using pack animals along steep cliff faces. To transport 30,000 tons of steel and heavy machinery to the ridgetops, a large-scale access road campaign had to be carried out. Engineers decided to carve into the mountainsides to create 26 kilometers of dedicated mountain access roads. This process was carried out carefully using pre-splitting blasting techniques to eliminate residual vibrations affecting the young Himalayan rock formations, combined with the immediate installation of steel mesh and shotcrete to stabilize the slopes. However, the steep mountain terrain with its continuous sharp bends made transporting full-length bridge girder segments impossible. As a result, engineers had to carry out on-site fabrication. The entire steel volume was transported to the site in the form of standardized modular plates. Right at the edge of the Chenab Gorge, a precision mechanical fabrication yard was established to cut, drill, and assemble structural components on-site before moving them into position for erection. To handle welds and difficult orientations within the confined construction space, the engineering team even developed a specialized rotating lever arm system that allowed entire girder sections to be turned into favorable working positions before being launched out over the open span of the gorge. Once the logistical bottleneck had been resolved, the next challenge lay in the geological foundation of the construction site itself. The Himalayas are a young tectonic zone, fractured and located within a region of strong seismic activity. The rock foundation along the Chenab Gorge was broken and unstable, making conventional foundation construction methods face the risk of the entire structure sliding down into the river below. To handle this complex geological structure, engineers were forced to adopt a strategy of designing and constructing simultaneously. Instead of carrying out large-scale excavation all at once, they removed the soil and rock layer by layer, combined with continuous geological analysis directly at the site. The entire fractured rock mass was then secured using a system of deep-drilled cable anchors. The decisive step lay in the use of high-pressure grouting techniques, injecting grout into even the thinnest cracks, transforming a loose mountain slope into a solid load-bearing rock mass. On this newly reinforced foundation, the two massive gravity foundations known as S40 and S50 were officially constructed. A huge volume consisting of 34,000 cubic meters of concrete and 5,800 tons of reinforcing steel firmly locked these two load-bearing structures into the mountainside. They not only serve to support the load of tens of thousands of tons of steel above, but also act as the core anchoring points that distribute the compressive forces from the bridge arch deep into the mountain slope. Once the two foundations S40 and S50 had been firmly anchored into the mountainsides, the vast open span across the gorge itself became an extraordinary challenge. At a height of 359 meters, engineers not only had to solve the problem of gravity, but also needed to provide a solution to aerodynamics. The V-shaped terrain of the Chenab Gorge unintentionally creates a venturi effect. When airflow is forced through this narrow corridor, wind speed increases suddenly, generating gusts with velocities of up to 266 kilometers per hour. Facing such intense aerodynamic pressure, conventional design options such as cable-stayed bridges or suspension bridges became ineffective. The structural nature of suspension bridges involves high flexibility, making them highly susceptible to resonance when exposed to strong winds. This continuous twisting and vibration is unacceptable for railway transportation, where trains require a deck system with absolute stiffness and stability. To completely eliminate oscillations, the optimal solution was a compression-resistant steel arch structure. Instead of relying on the tensile forces of cable systems, a massive steel arch with a span of 467 meters operates based on the principle of compressive load transfer. The entire weight of the bridge deck and the dynamic loads from trains are transmitted along the curvature of the arch ribs, transforming into compressive forces that are pushed outward toward both sides. At the abutments, the two gravity foundations, S40 and S50, absorb and dissipate all of these forces deep into the mountains. By fully utilizing the natural rock foundation, the arch structure forms an ultra-rigid integrated system, allowing the bridge to stand firmly amid storms that shake the valley without requiring any intermediate piers anchored into the riverbed. To assemble tens of thousands of tons of steel across a canyon deeper than the height of an Eiffel Tower, engineers could not erect scaffolding from the riverbed far below, and no ground-based crane could reach a distance of nearly 500 meters across the gap. With all support points from below completely eliminated, they were forced to deploy a giant cable crane system stretched across the sky to lift and install structural components in midair. As a first step, two temporary steel towers dozens of meters tall were erected on the two opposing foundation blocks to serve as anchor points for the cable crane system. However, pulling the first steel cable across the windy void was extremely difficult. Therefore, the engineers decided to carry out an extraordinary aerial solution. They deployed a specialized helicopter to fly across the canyon and release a pilot cable into the span to create the first guiding line. This thin cable served as a core guiding path. It was connected to a high-capacity hydraulic winch system to sequentially pull heavier cables, and finally to place the main superload cable onto the tops of the towers. When this 950-meter cable network was stretched across the canyon, cable trolleys running on the cables began lifting individual steel modules from the fabrication yard, gently sliding them out into midair, ready for the massive assembly operation. From this point, the main steel arch span, measuring 467 meters, began to be erected in midair using the balanced cantilever method from both sides of the canyon. Individual steel modules weighing dozens of tons were lifted by the cable crane system from the edge of the gorge, transported to their installation positions, and then temporarily fixed to the previously completed sections of the arch. After each installation step, the arch ribs extended several more meters into the void, gradually advancing toward the center of the Chenab Valley. However, as the cantilever length continued to increase, each arch rib began to enter a temporary state of imbalance under the combined effects of its self-weight and the strong wind currents inside the canyon. To control this condition, engineers had to deploy temporary stay cable systems anchored diagonally toward the mountain slopes, ensuring that each arch rib remained stable within allowable limits as construction continued outward into midair. This erection process lasted several years, with each steel component adjusted using high-precision geometric surveying systems to ensure that the two arch ribs advanced toward each other along the exact design trajectory. The allowable tolerance at the closure point was measured only in millimeters, because even a small accumulated deviation over a length of nearly half a kilometer would have been enough to prevent the entire structure from closing properly. Finally, when the distance between the two arch tips was reduced to only the last few meters, the central closure segment was lifted and installed into position. The moment when the two arch ribs met in midair not only marked the completion of the longest structural span of the bridge, but also turned Chenab into one of the largest railway steel arches ever constructed in the history of global bridge engineering. However, closing the steel frame was only half of the structural challenge. To ensure that this superstructure remained resistant to high-intensity earthquakes and Venturi wind forces reaching up to 266 kilometers per hour, engineers pumped self-compacting concrete to fill the entire hollow steel tube system, forming the core of the arch. This solution created a perfect composite structural system. While the outer steel shell carries tensile and bending forces, the solid concrete core inside resists the entire compressive force, while also increasing mass to suppress vibration and lock the arch system into a permanently rigid structural unit. Once the main arch had been completed and achieved maximum stiffness thanks to the concrete core system, the cable crane system continued to be used to erect steel support columns along the top of the arch. These columns formed the support system that would carry the entire railway deck. However, to place the deck structure across the windy valley, lifting each span in midair using cranes would have been too risky. Instead, the engineers applied the incremental launching method. The entire deck system was safely assembled and welded into a continuous structure on one side of the valley. After that, a massive hydraulic jacking system pushed the entire bridge deck forward into midair step by step, sliding it across each support cap until it reached the opposite side. Just as the mega project seemed close to completion, engineers had to confront the most invisible and severe enemy: temperature differences. The deep and narrow Chenab Gorge causes sunlight to fall unevenly across the bridge. One half of the structure can be heated by summer sunlight to temperatures of up to 50 degrees Celsius, while the other half remains in shadow at temperatures close to 0 degrees Celsius. This extreme difference causes the steel structure nearly half a kilometer long to expand and contract continuously and unevenly. If the railway tracks were rigidly fixed to the bridge deck, thermal stresses would immediately deform the rails and could derail any train traveling at high speed. To solve this problem, a mechanical design contrary to normal intuition was applied. The railway track system on the Chenab Bridge is not rigidly welded to the deck. Instead, the rails are designed to rest on guided sliding supports and are precisely pre-stressed. This intelligent sliding mechanism allows the rails to freely expand and contract, moving along with the breathing motion of the bridge rather than resisting it. As a result, despite the steel structure below continuously deforming under temperature effects, the railway surface remains perfectly aligned, ensuring absolute safety for trains crossing the bridge. In the summer of 2024, after more than 2 decades of relentless struggle against harsh natural conditions, the first test train smoothly crossed the Chenab Bridge. At a height of 359 meters above the river, the first passengers witnessed a breathtaking view never before seen in the history of railway engineering. But beyond the overwhelming beauty and those extraordinary mechanical records, for millions of people, the sound of the train whistle echoing through the Chenab Gorge carried a far greater meaning. It symbolized a permanent ribbon of steel connecting 2 territories despite the severity of nature. It transformed a valley that had remained isolated for centuries into a continuous economic lifeline, completely removing the geographical separation created by the Himalayan mountain range. Standing firmly in the windy skies of the Himalayas, the Chenab Bridge is not just a load-bearing structure, but the highest declaration of engineering intelligence. It confirms that, with precise core technology and a strategic vision, even the harshest geographical barriers must give way to become corridors of connection. If you are amazed by the mechanical achievements that push beyond every limit of the world's highest railway bridge, leave a comment below to let Mandarin Tech know. Don't forget to subscribe to the channel to continue exploring the mega projects shaping our world.